I would like to thank the organizer for giving me chance to present this talk today. So I'll talk about the active nematics, consist of a neural progenitor cell. So we study the induced integer topological defect. Sorry. Okay, so we study the two-dimensional cellular active nematics by using neural progenitor cell. This is almost same as a stem cell, neural stem cell. And this is in some sense, it's very, very clear ideal case. Because a cell elongates, has elongated shape, and if it becomes confluent, and they form local nematic order. And the cell move along long axis, and velocity reverse at relatively fast rate, about 1 or 2 hours. And at low density, you can see the cells are elongated, but no local nematic order. And the trajectory, they change direction from time to time. And in the confluent case, cells are aligned nematically. You see the nuclear motion, they move back and forth. And sorry. Okay. So in a confluent state, you see the nematic order. Cells are elongated. It's a very tightly packed. And the ideal case, this system doesn't have very strong cell-cell adhesion, not very strong adherent junction, and they don't have tight junction. They can move, they can slide each other, and they can pass each other. And then in this structure, we can measure the orientation of the elongated structure. And the color is coded between 0 and 180 degrees, and you can see the topological defect. So spontaneously, many topological defect, half-integer topological defect appears. They annihilate, but finally, after a few days, they don't move. Pattern doesn't move much, but the cell start to accumulate at +1/2 topological defect and escape from -1/2 topological defect. This was observed several years ago. As you see there, +1/2 topological defect cell accumulate at the core. By the way, right-hand side, you see the fluorescence image of the nuclei tagged by the M cherry. -1/2 topological defect, you see the relatively density is lower at the core. And the +1/2 defect moves towards the head of this comet-like structure. It's consistent with the prediction of the linear active force theory. And -1/2 topological defect doesn't move due to the symmetry. And so qualitatively, we explain this behavior by using simple linear theory. Simple linear theory means the active force is proportional to the stress. It's spatial derivative or divergence of the nematic order tensor Q. And if theta is positive, it's called extensor. And if theta is negative, it's called contractile. So this picture was consistent qualitatively. And so from this force field, we can infer that force is moving force. The velocity field is towards the head direction. And we also assume there is anisotropy in the friction. So if the cell can move easily along this elongated direction, but it's difficult to move into the perpendicular direction of the elongated direction, then the cell will accumulate at this core. That was a simple explanation. However, if we measure the fraction force, by using traction force microscope. The stress field around this commutative structure is contractile, so force is opposite, directing opposite to the moving direction. This is similar to the situation that Radu and Singapore group observed for MDC case cells. However, their motion is consistent with this simple linear theory. And this simple linear force is also used for many other more complete models, like active gel model or active liquid crystal model. So then, today's talk, so we study the behavior around +1 integer defect. So why +1 integer defect is interesting? Because that is important in morphogenesis, like hydra, mouth and foot formation. So it was discussed in this paper, and the +1 defect in active pneumatics does not appear spontaneously because it costs more elastic energy. So then split into 2 +1/2 topological defect. However, we can induce +1 defect by using microfabricated pattern on the substrate. For instance, this kind of +1/2 defect, the orientation of the particle or cell can be explained by this equation. Theta is the angle of the element, and phi is the coordinate, angle coordinate measured from the origin. And theta 0 is a tilt angle. So this defines the one parameter family of +1 defect. So by changing theta 0 from 0 to pi/2, so we can realize the spiral or counterclockwise spiral and then target the pattern. Then if we go further, we can define clockwise the spiral. Then again the Asta pattern. So this kind of the pattern, if we believe the linear active force relations, the force is predicted like this. So for the target pattern, if theta is positive, the force will be outward. And this is because for extensor system, in this kind of bend structure, so cells tend to extend more. So the bending perturbation will be enhanced due to this extensor property. So then the simple prediction by the linear theory says that if theta is positive, by simple calculation, we obtain this. S is a scalar order parameter, and theta 0 is a tilt angle. If the tilt angle theta 0 is smaller than pi/4 for theta equal positive case, then the cell will be attracted to the core. However, if theta 0 is larger than pi/4 for extensor case, then the cell will be depleted at the core. So this simple theory, linear theory, predicts that the attraction or depletion is a dichotomy. This is just determined by the sign of theta. So, however, we observed a very contradictory result. So this is our experimental system. So we designed the micro pattern on the PDM substrate. So here the reach is spacing is roughly 60 micrometer, and height is only 1.2 micro. And at this very shallow ridge, cell can easily crawl over ridges. However, they tend to move along these ridges but they are free to ride over these ridges. So by using this, we can apply some kind of external force to the pneumatic order. So this is our system. So we can design many different +1/2 defect in the one dish, for instance. Then we can obtain a lot of good statistics. Then, okay, this is a main result. So for instance, for the circular target pattern, we observed the accumulation at the core of the +1 defect, target defect. You see the motion of the nuclei, and they are essentially moving along this tangential direction, theta direction, phi direction. However, they gradually tend to move towards the core of the target pattern. And this was observed not only for target pattern, of course, aster pattern, all spiral pattern attract the cell towards the core. And this is the final, for instance, density distribution as a function of radius and log-log plot. And here you see the different pattern, aster and clockwise, counterclockwise spiral, and the target and clockwise spiral. So after 2 days, you see that all the pattern attracted cells at the core of the defect. So this is very contradictory to the prediction by linear active force theory. And so next we checked how the orientation of cells are aligned to the pattern. And at first we measure the orientation of the cell and compared with the background pattern on the PDMS. And this is the scalar order parameter measured from the orientation of the cells. And of course, at the core, scalar order parameter decrease. It should go to 0, but you see maybe it doesn't go 0 because of some finite resolution. And the angle difference between cell elongated direction and the pattern are very small. This roughly plus minus 5 to plus 3 degrees.
Sorry?
And the average, it's angle difference between, yeah?
Sorry, could I ask a question? Yeah. Just for comparison, what happens when you place these cells in a well that doesn't have any ridges at all? Does the density stay completely uniform?
Oh, we have the local pneumatic order and like this.
Okay, and so if you have them in a little dish and there are no ridges, then the density stays uniform, they don't form a core or anything like that.
Yeah, but okay, in the beginning we have more disorder, many defects, but gradually they annihilate. But this Q pattern, orientation pattern, doesn't move fast compared with the cellular flow. So after a few days, pattern is almost fixed. But the cells are only moving along this direction, then accumulating at the +1/2 defect. So the pattern motion is slow and compared with the cell individual motion and cell net flow. Okay, so and then we found some small clockwise chirality between the background pattern and the measured orientation of the cell. The difference is about -5 degrees. And what about the cell velocity? So cell moves back and forth along the elongated direction. the velocity, instantaneous velocity is about 0.5 micrometer per minute. And this reverse orientation in about 1 hour. However, we can also do the long-term time average of the drift pattern, drift velocity. And also we can coarse grain the cellular flow. So if we average for 10 hours, the velocity, resulting velocity is about 10 times smaller, 0.05 micrometer per minute. But there is some net flow. In the case of target pattern, their cells are moving along this azimuthal direction, but there is the consistent inward flow toward the core. And this is incompatible with simple linear theory because we know that from the motion and the behavior around the Planck have defect, theta is positive. However, this is incompatible with linear theory prediction. It's same for other pattern, the radial pattern or slightly curved spiral pattern. And we all see the inward flow, net flow. And this is the net instantaneous velocity as a function of radius. This is the correlation function of the orientation change. So they exponentially decay this correlation function. And how is the net velocity, radial velocity? Net velocity is toward the origin, so the VR is negative. And this shows the angular distribution of the velocity field, net velocity field. So you see there each pattern, each spiral or target pattern, there is sharp peak. So we measured this peak position of the net velocity. And this angle of the velocity field relative to the direction to the origin is plotted as a function of the tilt angle, theta 0. So here we change from target pattern, spiral, and after spiral and target. And they all lies on this hatched region. Hatched region is the flow is inward. If velocity field, angular velocity field relative to the origin direction is less than plus minus 90 degrees, the flow is inward. Outside here, outward. And this broken line is a prediction by the linear active force model. So even if I assume the anisotropic friction, we should see some outward flow at highly bent spiral or target pattern. However, in our case, all the patterns show the inward flow. Okay, so maybe I should skip this. Just I want to mention that there are other possibility, we consider other possibility, but there are no chemotaxis and no isotopic contraction, and there's no MIPS. So we measure the velocity as a function of density. This doesn't satisfy the MIPS condition. So what we did is a bottom-up approach. So we consider the particle model, which has a nematic alignment and velocity reversal and repulsion effect. And from this, we apply the Boltzmann-Ginzburg approach, then obtain the continuous model. And from this, from the particle model, we can obtain the coefficient of the continuous model. To make a long story short, the final result is active force obtained in this approach is like this. We have two extra active force. So this is a linear active force. Then we have two nonlinear terms, nonlinear in Q. And this term, of course, should satisfy the symmetry of the system. And the good thing is all these coefficients are determined from the particle model coefficient. So this, I can go quickly. So the particle model is, we use a dry active nematic model by Patrick in 2019. Essentially, it's similar. Just we apply the external field. We consider the PDMS pattern as a weak external field. So we have the velocity reversal, nematic alignment, and external field, and some soft repulsive torque by the other particles. Then we did the simulation around the plus one defect. So I don't show the movie here, but so we studied many different plus one defect, and this is phase diagram as a function of instantaneous velocity of the particle with zero versus the repulsive interaction, repulsive parameter. So red region is attractive. The density is high at the core, and the blue region is depletion. So for larger V0 and smaller repulsion, target pattern can be repulsive, but otherwise attractive. So Asta pattern is mostly attractive. Only for very strong repulsion, it can be repulsive. And there are a lot of coexisting regions for the attractive state for different plus one defect with the same parameter. And the continuous theory, they often use the Fourier mode for the one particle distribution function, F, and the first Fourier mode, F0 density, F1 is rho times V at the velocity, F2 is rho times Q. But this, and we have this external force. But this is not so easy to understand. So we rewrite this Fourier mode into the vector tensor form. Then it looks like very much like the Veris-Edward equation, which is used for active nematic theory using liquid crystal theory. So the only difference is, the largest difference is this nonlinear active force term. This is linear. And this term corresponds to the anisotropic friction. There is a shear effect and rotation and some, this is the compressive system. So we have some extra term for due to compressibility. So, by the way, this one of this term has been discussed, introduced by Vaitra, Marchetti, Ramaswamy in 2018 for wet active nematics. They discussed this will stabilize the bending deformation in extensor system in 2D system. So this is just an example of how this PDE shows nematic chaos. And in the homogeneous nematic state, we see the annihilation of the topological defect, and finally, we see the density become higher at plus 1/2 defect and lower at minus 1/2 defect. And for the Asta pattern, it's simple. So here the cell accumulate in this red region. For target pattern, here, for instance, again, the density is higher at the core. And this phase diagram for target and the aster in a full PDE, and then this is the almost conclusion. So we have now these two nonlinear terms. This is crucial to explain this behavior. So to even further simplify the model, we assume that Q is slaved by external field and assume there is no evolution, time evolution of Q. And now Q is fixed by the external field. Then also we assume the steady state for the velocity. Then now the force field is determined by this linear force and nonlinear force. Then this is the final result. So if we assume the axisymmetric case, the force, linear force can be written like this. The theta is linear active force term, gamma 1, gamma 2 is the coefficient of the nonlinear force, and there's a density times S, scalar order parameter. And at the transition point, there is no accumulation and depletion. So at transition line, density should be constant, uniform. So we can assume this density and rho is in the equilibrium or condition, steady state condition, uniform condition. Then the now new diagram looks like this. So previously we have only theta. So theta, whether it's positive or negative, determining whether the system is extensile or contractile. However, we have now vertical axis is proportional to the gamma 1 minus gamma 2. Then we have a new regime. Here, for instance, regime, these two, both target and aster pattern can attract cells. And regime 4, both target and aster can repel cells. So in this, with this nonlinear term, we have 4 different regions, not only dichotomy between simple extensile and contractile. Then our experiment corresponds to this regime 2. So, and just to give some intuitive meaning of this diagram. So for simplicity, if we assume the scalar order parameter is 1 and the density is constant, then we can write down the Q in the director using director. Then we have this some well-known bend deformation and spray deformation. And this A is this coefficient of theta, linear force term. B is gamma 1 minus gamma 2. And coming from this, this looks like anti-symmetric to the bend and spray deformation. And so it's cannot be derived from the divergence of stress. However, that can generally exist. And in this simplified diagram, in the spray and the bend, so these 4 states can be classified in this. So, okay, maybe I already used 30 minutes. So this was measured in the experiment. We apply Bayesian inference to obtain all the coefficients from the data of density Q and W. Then we found the only WQ cannot explain. We need to consider the 2 nonlinear terms. Then this is a fitting result. And this result shows not only the angle of the velocity, but the amplitude of the velocity profile as a function of tilt angle agrees very well. And so even if for target pattern, even if the linear force term goes outward, these nonlinear term, both gamma 1, gamma 2 term are directing inward. for the aster pattern, all three patterns are directly inward. So in our case, the sign satisfies this condition. And this is not only observed on the PDM's micro pattern, but it was also observed in the natural pattern without inducing by PDMS. In the natural pattern, by using this framework, we obtain the same coefficient satisfying this relation. Okay, this is the conclusion. Thank you for your attention.
Questions for Masaki? I think we can start here.
Hi, thanks for a great talk. So I have two very quick questions. So regarding so in your experiments, you saw these negative defects also, right? So you have like positive, negative, blah, blah, blah. Is there something that you see that is similar to the minus 1/2 defects in this case? So do these things, and did you also calculate it? Because in the end, I assume it's just a change of sign, and then you can have the same nice diagram that you had in the end, right? We have one region of attractive.
Oh, okay. We didn't. We haven't analyzed the minus one defect, but in this plus one between the
Plus.
target and target, we have the region where the minus one defect appears. There the density is lower. We know that.
I see.
So far we didn't test all the minus one defect. Yeah. So the simulation shows the minus one defect is depleted. But it's not axisymmetric. The density distribution is not axisymmetric. That is by simulation.
I see. And one more quick question. So did you see like what is the backflow of these positive and negative defects in the usual case? Like with this stress, you have a new stress essentially, a new force, right? So you could go back and calculate the backflow generated by that stress and see what happens in the usual equations.
Backflow is the flow prediction is maybe I can show that this kind of flow is the predicted by this coefficient. Yeah.
Thank you.
All right, let's take the question there now.
Hi. So just based on your predictions, can you lower the density of the pattern of the cells, and then these nonlinear effects should go in, and then do you see expulsion from these target-like defects? Right, in your phase diagrams, and the nonlinear terms come with the mean order parameter or the mean density. So if you lower the density, you'll go back to the region in your phase diagram. So if rho naught is lower in your experiments, you'll go back to the switching.
You're right. If density is low, then this term is not so effective. Yeah. But okay. Just mention that the S is mostly the very well ordered. S is close to 1 in our case. And density, if it's a confluent, it's not low, maybe, but they just at low density, maybe this term is not effective, but our data shows most of the case density and S is high.
But is it possible to do experiment, or is there like an experimental limitation why you can't do that?
So some movie shows from the beginning, you see some cells are already attracted to the target pattern. So it means there will be some effect, similar effect even at the low density. This one, I don't know, or this may be already high density. So this kind of pattern, at the low density, we see some attraction. So,
thank you.
So.
Let's come back to this side again.
I want to again raise the question of microscopic mechanisms. What do you think cells are doing to enact these nonlinear active forces when they're surrounded by other cells?
Oh, this, I don't know whether this is enough or not. This nonlinear active force, the meaning is related to the bending and spray. So this gamma 1 is positive in the most of the case in this particle model simulation. Gamma 2 is negative in this particle model. And both are, for target pattern, for bending, this gamma 1, gamma 2 time gives an inward force. And also spray pattern also gives an inward flow. This is just active force coming from this nonlinear term is directing towards the core in our case for both bending and spray pattern. We don't know other systems.
So cells essentially, so the idea is that if I'm a neuron and I'm crawling around, I adjust my active force based off of bend and splay, potentially elastic, Frank-elastic parameters around me to, that eventually directs me inward. All right. Well, anyway, I'll chat more offline.
Sorry, I don't know, but maybe they don't like the bending for shape. If they're bended, they tend to become more straight and maybe to reduce the bending perturbation.
Yeah, that's good for discussion later on. Yeah. So, Sriram.
Yeah, I had a couple of questions here. One is that you introduced two parameters in our 2018 or whenever it was. We pointed out essentially that if you're in a situation where there is a substrate, the active force does not have to be the divergence of a stress. Therefore, these terms are permitted. You can derive these terms from some fairly complicated things in a bulk momentum conserving system, but that's a separate point. What I was trying to figure out is that we ended up needing only to introduce one parameter extra to distinguish between the response to bend and the response to splay. So finally, is it essential for you to have both QDiv, Q... Okay, sorry, in your second term, in your gamma 1 term, the outer Q is contracted with the gradient?
Yeah.
I see. And in gamma 2, it's contracted with the free... one of the free indices on the Q inside. Yeah, right. I see. So do you end up needing them both in order to account for your effect? Do you end up needing both gamma 1 and gamma 2 to account for the effect that you're talking about?
Yeah. In fact, gamma 1 is more effective. Gamma 1 is a more stronger effect in our experiment.
I see. But when written in terms of the director field, it reduces to a single combination gamma 1 minus gamma 2, right? When you rewrite it in terms of the director? Can you just show that term? I'm just missing something.
So, but these two terms are almost similar, just.
No, so finally, in terms of director, one of them contributes to, and they both contribute to the difference between those two, or which? So your combination B.
These two terms in this director representation has the same term, and then this becomes gamma 1 minus gamma 2.
Okay.
So if the density and the Q doesn't affect, the two terms give the same contribution.
Okay.
Just sign is different.
Right. Okay.
And next question, Fritjof.
Yeah, so I was wondering about the microscopic mechanism underlying this. If I understood correctly, it's the fact that the cells move back and forth. So myxobacteria, for instance, also do this. Would you expect that in some regime, if you do this with bacteria that have this back and forth motion, you also see these effects? And sort of related to this, how much do these cells move back and forth relative to, let's say, their size before they turn around?
This velocity reversal is important. This is the coefficient for gamma 1, gamma 2, and the linear term theta. The velocity reversal rate is A, so it appears only in gamma 1. In this simple particle model, Hartley's model. Gamma 2 is always negative when particles are repulsive. B1 is a repulsive strength kernel. And
so when the reversal rate goes to infinity, then there's still terms left.
mean zero, you mean? No reversal rate?
Well, then it's a polar medium, but if it's pure, sort of, if it goes to infinity, so that it effectively
in
becomes
polar
analytic.
case, A is zero.
Yeah.
No reversal.
Sure.
But then still the alignment is nematic. So it's not completely polar.
Yeah.
But Carsten Kruse and their group also use the similar equation, but they have a polar and nematic order, and even the polar system, they have they can consider similar term. And but maybe polar effect is more stronger in the polar system. But here the polar order appears only after the cost graining, but after some time averaging.
Right. Yeah.
And
All right, then last question.
Perhaps a naive question, and just for my own doubt clearance. So, so your cells, even though they're surrounded by fluid, I think they're still crawling on a substrate. And what I understood was like these definitions of extensile and contractile, they are purely hydrodynamic. Like you talk about the flows. So I'm just confused, like how relevant is it to use these definitions for a frictional kind, like for these kind of systems? Because there's a lot of momentum dissipation going on as well. So for example, I don't expect these words to be used for purely granular system where there's no fluid medium around.
This Sinha Ramaswamy's PRL paper, if you have a force dipole, and then you can obtain this linear active stress term. But in our dry active nematics, maybe we can consider the force dipole of each cell. Maybe force the acted by the cell to the substrate or to the neighboring cell, because there are no net force each cell from outside. So it has to be force dipole at the lowest order. So they are interacting with each other, also with the substrate. So the contractile or extensile is also maybe.
So those definitions are relevant in those systems. Maybe I'll chat.
Just so we don't have a momentum conservation like wet active nematics.
I see. I'll chat with you later.
Yeah.
Sure. Thanks.
Great, and that's perfect timing. So let's thank Masaki again. And we now have the lunch break, and we restart at 2 with the afternoon session. Enjoy.